Welcome to the week 8 material. We are going to have a short video here about just reminding ourselves about some properties of the natural numbers we know very well. The reason we're doing that is because they will be very useful for illustrating how proofs can be written down in the sort of formal language that we set up using predicate logic. So it's some more practice of predicate logic and some reminding ourselves of what real numbers do. So real numbers. So the way that I've been talking about them so far is just in terms of numbers with a decimal expansion. Now that's not very precise, but it'll certainly do for what we are interested in here. So real numbers are just the set of numbers with a decimal expansion. Right. And we're going to think of all of the decimal expansions as giving different real numbers. With one exception, essentially one exception, except we identify 0.9 recurring. So this is the same, this means 0.9999, etc. That we are going to make equal to 1. So once I make this identification, then that gives me the idea of a real number accurately. And of course, we can have positive and negative real numbers. Right, one feature about the real numbers, which is not a feature of the complex numbers, is that they are totally ordered. So you can stick them in a number line and you can say which one is bigger than or equal to another one. So we have a relation which I can write as less than or equal to on real numbers. And I can tell when this holds between two real numbers by looking down the decimal expansion. So when are two numbers equal? Well, either because you've got this going on, so 0.4 and then a load of nines, that's the same as 0.5. But if otherwise, there will be a number that isn't just different in the decimal expansions because of these a load of nines, and then you can see which one's bigger than the other one by just seeing where it changes. So if you've got two positive numbers, then you just look down both of them along the decimal expansion, and the first one where they're different, the one with the bigger number is going to be the bigger number in general. So on two positive numbers, we know either that they are equal or that the decimal expansion is different and in the first place from the left, and x is less than y if the leftmost different digit is bigger in y than in x. Okay, I mean that's a lot more complicated somehow to say than to understand. Anyway, let me just write down some properties of this relation which hold, and I'm going to do it in the sort of predicate style language that we've done in the last week. So, properties. So, for all x, so I'm always working in the real numbers, so these for alls are taken over all the real numbers. For all x, x is less than or equal to x. That's called reflexivity. So obviously x is equal to x, and so x is always less than or equal to x. There is a nice property that is called anti-symmetry. For all x, for all y, we can tell when x is equal to y because x has got to be less than or equal to y, and y has got to be less than or equal to x. So it's obvious why, if they're equal, both of these things are going to hold, just by definition of this thing. But the other way round, it's true, because this is saying that there is nowhere that the decimal expansions are different. So that is called anti-symmetry. Very important condition here, which is transitivity. So if I take three numbers, x, y, and z, then x less than or equal to y and y less than or equal to z, that implies x less than or equal to z. Right, so the way to think about this, first of all, that's called transitivity. And the way to think about that is if you think of a number line and you've got x here and you've got y here and you've got z here, then this is saying that x is less than or equal to y, this is saying that y is less than or equal to z, and then the whole thing together implies that x is less than or equal to z. So this one is in that relation as well. So that's an important one to know. And then there is one more thing, which is the total order relation, and that is just saying either x is less than or equal to y or y is less than or equal to x. For all x, for all y, either x is less than or equal to y or y is less than or equal to x. And that's total order relation. Now that is a property that is certainly not inherited by the complex numbers. Okay, so let us talk about right, a couple more things that we're going to want to know. One is just that there are other relations using the same idea, which give us symbols that we know. So we also have x less than y, which is the same thing as saying that x is less than or equal to y and x is not the same as y. Okay, so there is that symbol, and obviously you can put them the other way round, and x bigger than or equal to y, etc. The only reason to want to write those down is just so that we know how they behave with respect to negation. So we have not x less than y. So this is a formula which is true or false depending on what x and y are. But not of that is the same thing as x bigger than or equal to y. Right? If you have a number line and you've got x and y in that relation, so x is definitely less than y, then the opposite set of things that you could be looking at there are all the things that are the same as y or bigger. So you have those relationships. Okay. The other thing we want to say is about the arithmetic properties. So these are going to be useful for us as well. Arithmetic properties of the reals. And that's just means addition and multiplication and the properties that they have. These are actually the properties of being a field. So we have operations plus and times, and what do? Well, if I take A plus B, that's the same as B plus A. I'm not going to write down what these are called, but you've seen some of them before. This is commutativity. We saw that with Boolean algebra. This is basically saying if I've got brackets around sums, I can just take them away. It doesn't matter what order I write things in. So that's called associativity. And you can check all these things by thinking about the decimal expansions, but we're just going to get them done. There exists a number 0. So this is a constant in the theory. A plus 0 equals A equals 0 plus A. So this is just a number with the decimal expansion being all zeros everywhere. And you can find a number. So there exists some minus A. And what does it do? Well, if you add A to minus A, you get 0. And it doesn't matter, of course, which way around you do that. Okay. And then that's all we want to say about plus. And what about times? A times B is B times A. Doesn't matter which way around you multiply. Similarly, we have this associative property. We can move brackets as we like. We have, so there exists a number 1 such that it doesn't matter which way round you do it, but multiplying by 1 gives you back A. So multiplying by adding 0 gives you back A, multiplying by 1 gives you back A. And as long as A is not equal to 0, if A is not equal to 0, then there exists, we can write it in different ways. 1 over A, it's going to be the same thing as A to the minus 1. And what's it going to do? Well, it just multiplies by A to give you 1. And there's one more thing that we need to say, which is just how multiplication and addition interact with each other. So all that is you can expand brackets. So A times B plus C is equal to A times B plus A times C. And you can expand brackets either way round, of course. Now, there's one more thing I just want to define, which is the operation of taking the absolute value. So this is useful for breaking into case-by-case checks. If x is a real number, then x denotes the positive version. of x. So what does that mean? That just means that we are going, if x is negative, we just make it positive. So the absolute value of x is defined. So this is a function on x, and it gives us back x if x is bigger than or equal to 0. Otherwise, it gives us minus x if x is less than or equal to 0. So that is a function. It is the function that makes x positive whenever it goes negative. And we just have one interpretation which is sometimes useful, which is that x minus y is the distance between x and y. Okay. Those are all the properties we need to be able to start getting involved in proofs, which will be the next video.